learning or induction problem is really old philosophical problem, so philosophers have been thinking about this for a couple of millennia at least. And they have actually come up with some useful principles. Don't always do that. And there's Occam's razor, which says that if you have multiple hypotheses that are all consistent with your data, you should generally prefer the simplest of them that is consistent with your data. So for example, relativity theory might sound like a super complicated theory, but it's actually the simplest theory that's consistent with observational data about these things. So this seems to work pretty well. Epicurus is this ancient Greek philosopher who has almost the opposite principle. He says that if you have multiple hypotheses that are all consistent with your data, then you need to keep all of them. Because if you don't have any data that discards your theory, then you must keep it. You must keep it as a possibility. Does this principle make sense, I think, in your opinion? There's also Bayes' rule, which says how to update your belief in a hypothesis given some data. And the input to Bayes' rule, the crucial input, is the prior, what's my prior probability before seeing any data in the hypothesis, and what class, this curly H, should I consider? What is the class of all possible hypotheses? These are the two sort of crucial inputs to Bayes' rule. If we have these inputs, the likelihood is usually easy, and we can know exactly how likely we should consider a hypothesis given our observational data. So Bayes' rule is really great, and it's been very influential, but it does rely on this prior, knowing this prior, and knowing this class of hypothesis. So how can we solve these problems? What is the class of hypothesis, and what is the prior? The answer to these questions come from a kind of unexpected directions. Alan Turing invented this universal Turing machine. Machine basically can compute anything that's computable, also known as programming language. So what we can do with these Turing machines or programming languages is we can say that a hypothesis about the environment is just a computer program. Since computer programs can do anything that's at all possible to do effectively, using computer programs as hypotheses, we're basically considering all possible environment hypotheses. So we're very much in line with Epicurus' principle. Another neat thing about computer programs is that we can check if a computer program matches our experience so far. So let's say we've encountered some history, we've taken some actions, A up to time t, and we've seen some percepts, E up to time t. We can check if a given computer program is consistent with what we've seen so far, simply by giving the actions as input to the program and checking whether the output is exactly the percepts we've seen. If the output of the program exactly matches the percepts we've seen, then we say that the program is consistent. And if it is, then it's a consistent hypothesis, and if it's not, then we discard it. Similarly, if we want to use a computer program to predict the future, we just input the next action we have in mind, and we check what is the output percept from this program. So this way we can use programs to predict and to plan. And finally, a really neat thing about computer programs is that they have a length. It's just like written in some programming language, and we can just check how many bytes did it take to write this program. And that's what we call the length of the program. And we can say that the prior probability of a computer program P being the true environment should be 2 to the negative length of the program. might seem a little bit arbitrary, but it isn't. So combining all these principles, we get Solomonov induction. Solomonov basically combines Epicurus principle, use all programs. Occam's razor weights simple programs, short programs, higher than long programs. Obviously covers the areas of Turing and Bayes' rule in how to update the belief in the computer program based on data. Yes, question?
The environment is usually, it would lead to a stochastic perception.
Right.
So a computer program would also have to incorporate this stochastic
Right.
feature. So how can you check it for consistency?
Right, that's an excellent question. So we built this induction principle based on computer programs that are deterministic. And I will show you a result in like the next 2 slides, which shows that despite we base this principle on deterministic programs, they still handle stochastic environments really well, which is really surprising and like pretty cool. So, but that's in the next 2 slides. First, let me just introduce this Solomonov factor universal distribution. So the universal distribution, universal probability of seeing some preset sequence, given some action sequence, is just the sum over all programs, and the programs weighted by 2 to the negative length, the prior probability. Let me just give you an example of that before going on. So for example, seeing 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, given that I take exactly those actions, that's a high probability, because there's a simple computer program which outputs exactly this preset sequence on this input sequence, namely the program that just mirrors input to output. So seeing something simple, or seeing something that's very predictable from the actions, that has high probability. In contrast, seeing something random has comparatively low probability, because in order to have a computer program that outputs exactly this sequence on this non-informative input, you must include the entire sequence inside the computer program, and that's going to make the computer program long. So a priori, it's less likely to see random sequences than structured sequences. Question?
So if I remember correctly, the length is a strong function of how you choose to represent the program.
Yes.
Have you figured out a general way to represent that gets around that limitation?
Right. Our standard answer to that is that you should use some natural programming language, say C or Python. But there is certainly some indeterminism there, like which programming language to use, and it can have impacts. Yes. Right. So that's some examples. Basically, structured environments are more likely because they have short computer programs. So, yeah, we follow basically Occam because we have simple program high weight. At Curious, we have all programs based on how we discard programs, ensuring how we can do environment. Already basically said that. One thing is that what we're usually interested in is to predict the next preset given some history and action. And we can compute this conditional probability with just the standard rule of conditional probability. So with that in place, we can now describe this very impressive learning result by Solomonov. It's very unfortunate that the red is almost invisible. So it's n of 0 given the history minus mu of 0 given the history. I hope you can almost read that.
Can you turn off the front lights or anything like that?
Oh, that's a good idea. Any idea how?
There are lights
the true distribution mu with 0 given basically. So what this theorem states is that you take any computable environment mu, you don't know it, and you interact with this environment mu by taking action and seeing percepts. And then you compare what probability does the universal distribution give to the next percept being 0 to the probability that the true probability of the next percept being 0. And what happens is that these two estimates converge fast. So the Solomonov prediction will converge to the true environment's prediction very fast.
So what's K of mu?
K of mu is the complexity of the environment, the Kolmogorov complexity of the environment. So the bound is weaker, the more complex the environment is. So K of mu is basically the shortest computer program describing mu. So we can say that the prediction error at time t, that's like the different probability, how different is the universal probability of the next percept from the true probability of the next percept. So that's the prediction error that the universal distribution makes. And I'll try to plot them here. In the beginning, M doesn't know anything about the true environment mu, so it will predict something which isn't related to the truth. But pretty soon, the prediction of M will converge to the truth. And the convergence is so fast that the total error, the area between these two graphs, will actually be finite. So you act in this environment for an infinite lifetime, and the total error you make of your entire lifetime is finite.
Wow.
Yes, question?
What about in non-stationary environments where you capture all possible ways the world can change from the beginning?
Yes, even non-stationary environments, they can be really any environment. Any environment that can be described by a finite computer program, a computable environment. Yes?
When the number of history samples just go up each time it takes an action and then just the whole system grind to a halt over time?
Sorry, once again, I didn't hear you.
So as it takes more actions and it builds up more histories, it's going to adapt. But then each time it has to perform a search, it has to go through a larger number of histories. So won't it eventually just grind to a halt?
Are you concerned about computational aspects?
Yes.
Yes. Yes. This is not very efficient. This is more like it's in fact incomputable to compute M. The value of this is more that it gives a conceptual and like mathematical understanding of what is the right thing to do. That's the goal. And then like in the second part I will describe like how we can approximate this. But for now this is not computable, not really practical. Anyway, an agent that is based on this universal distribution can basically learn any computable environment. And this result works amazingly even if the environment is stochastic. Even though M was based on deterministic computer programs, it still works in stochastic environments. Yep.
K of mu cannot be infinity as well.
If K of mu is infinite, if the environment cannot be described even by a stochastic computer program, then just the result is vacuous. If the right hand side is infinity, then the bound is vacuous.
So does a stochastic computer program then assume a random number generator, a real one? Is that how to understand how you get a finite number of errors in a stochastic environment?
Right, so the point is that you don't need to say what the correct next bit will be. You don't need, let's say the environment is a coin flip environment, right? So the environment every time flips a coin. But then the environment doesn't know either what the next bit will be. So the environment gives 50% probability to heads, 50% probability to tails.
All you have to do is produce that distribution, not
Yeah. So all you need to do is to produce a distribution. Yeah.
So this K is the complexity of the programs, and so how do you decide that? Is that a how do you define that complexity? So
Right. So K of mu here, that's the Kolmogorov complexity of the environment mu, and that's defined as the length of the shortest computer program that computes mu. More questions? Okay.
It's perhaps a better question when we get to your actual approximation.
Ah.
But if you run into two programs for K of U, both of which are similar, like same or very similarly sized,
Okay.
what in your framework is the decision structure between picking them for the sake of the model? Or does picking between them not matter for the sake of the model?
Either they're going to be functionally equivalent, in which case it doesn't matter, or they are going to be different, and then at some point you are going to distinguish between them.
Okay, but is it just, I guess, up to the history, the way it plays out, then which one is chosen?
Yeah, pretty much. Yep.
Could you remind me what 0 is the value of? Yeah. That's E of t.
Yeah, that's E of t, right? What is the probability that E of t is 0?
So here it's are we assuming that the environment only ever gives us a 0 or a 1?
Yeah, that's implicit too. Yep.
So my understanding is you can get some pretty good random number generators with some pretty short programs.
Right.
Is this algorithm actually good at figuring out a program of random number generators?
Right, because this just assumes away all the like computational complexity theory stuff. In practice that would be really hard, but in theory it's easy.
Meaning you need a tremendous amount of data.
Yeah.
I see.
Or rather a tremendous amount of computation power. Yeah. So I think we should move on. So we have this agent and it can learn any computable environment, which is really great. So what should it use all this knowledge for? The answer we give to this question is it should maximize reward. So we assume that the percept that the agent gets every time step is composed of one observation part and one reward part. And the reward part is just a real number between 0 and 1. So for example, if this is a robot, the observation will be like some visual image, and the reward will be a number indicating how happy its human owner is with it at this point. Another example is of the DQ learning algorithm, DQN, playing Atari games. In this case, the observation was just the screen of the Atari game, and the reward was the score of the game. So the goal of the agent is to maximize the return, that is the sum of all the rewards it's going to get in the future. And to make sure this sum is finite, we introduce this discount parameter, gamma, which is less than 1. And then we downweight future rewards by gamma. So the first reward is fully weighted, the second reward is multiplied by gamma, the third reward is multiplied by gamma squared, and so on. So it's a geometric discount. This ensures the sum being finite. And it also makes the agent care more about the near future rather than what happens 1,000 years from now, which is generally good.
And what's wrong with infinite reward? Oh, sorry,
Right.
infinite return.
Yes, what's wrong with infinite reward? One problem is that in that case you get the same infinite sum if you get 0.1 reward at every time step as if you get 1 reward at every time step, because both are infinity. So it's hard to compare infinite sums. Yeah, it's much easier to compare finite sums. Yeah, that's a good question. One more thing I wanted to say actually about this slide is that you can basically encode any goal as a reward signal. You just give the agent reward for doing the goal and no reward for not doing it. Reward for winning the chess game, no reward for losing the chess game. reward for giving me a beer when I'm tired, no reward for not doing it. So, yeah. So basically any goal can be formulated as this reward. So we're still general. Right. So a return, that's the sum of all the rewards, and the expected return, that's called value. So the value of an agent pi, or policy pi, in an environment mu, that's just the expected return that the agent gets following this policy pi in this environment mu. So one way to think about this is like through these recursions, the value of being at this top node, that's the value of being in this node that you get after taking your first action. And the value of being this point that you get to taking your first action, that depends on the whatever the environment gets to, which node the environment gets you to, with what probability, and then you sort of average over the values of those points below and so on. So, yeah, it's basically just expected return value. It's a standard reinforcement learning concept. So the agent tries to be good in expectation, basically. Finally, the planning part of ICE, the last component. It's really quite simple, much simpler than the learning part. With this discount parameter gamma, we get what is called an effective horizon. So basically what happens with these geometric sums is that the tail of the sum, all the elements after some point m, this entire tail will be almost zero because the gamma pushes this part of the sum down to zero so fast. So the return for some infinite future is basically the same as the return for the first m time steps from now. This makes planning a lot easier because you just need to look m time steps ahead, and you can just think about all the things you can do within those m time steps, and you can think about the best thing to do, and yeah, that's the best thing to do. So conceptually, planning is actually very, very easy. I'm not saying this is a computationally efficient way of doing planning, but conceptually, it's easy to find the right thing to do in this setup. Another way to express this principle for planning is to say that the optimal action is the output of this formula, where basically always take the best action with the max operators and expectations with respect to the environment with the summations and probabilities.
Did you say earlier that this policy may not be computable?
Yes, I mean, if the environment mu is computable, then you can find optimal policy here.
Yes.
Yeah, but what I'm going to get to right now is putting all these things together, and that's called ICSI, because in the real world, we don't know what the true environment is. So the idea is that we replace the true environment mu, which is unknown, with this universal distribution n, and then we tell the agent to be optimal with respect to the universal distribution n. So the policy ICSI is the best policy with respect to the universal distribution n. Since this universal distribution n learns any computable environment, being optimal with respect to n is, after a while, the same thing as being optimal with respect to true environment. At least that's the idea. So basically you get this one-line formula, which is like the thing below there, for the optimal behavior in an unknown environment. And here we've been basically tying together the Solomonov induction, maximizing reward, and this simple planning mechanism, expect max. No, it's not computable. learn in computable environment. What we do is we basically act base optimally with respect to base rule. I have this one equation for artificial general intelligence, and the only thing that prevents us from taking over the world is computation. Yeah.
The other would be a policy to establish what the rewards are for action.
Right.
Yeah.
That is not an easy question either. Sure.
There were some examples of how to establish a reward system.
Right. I mean, if you have a chess playing agent, it's easy, right? You just give it reward for winning and no reward for losing. If you want a more general agent, the way I like to think about it is maybe I have a button that I can press, say, every hour. I'm so and so happy with you right now. And then the agent just tries to learn what does Tom like, and if it's really intelligent, it's going to be really good at predicting that, and it's going to make you super happy, ideally. So, there's like some questions and problems with this project.
Could the rewards also be outsourced to some sort of like cost benefit analysis thing, so that in like a more real world simulation environment, rather than just having you did good, you did bad, you have more nuance, you did mostly good, or you did pretty damn bad, but not completely terrible.
Like, this reward doesn't have to be 0 or 1.
Right.
It can be any real number in between.
Right.
So yeah, you can like have a graded response, yeah. Yep.
So, it sounds like in any kind of real practice, in any kind of even toy universe that kind of simulates the real world, it's going to make the kind of mistakes that does the things that please you now but doesn't recommend you brush your teeth.
Right.
And 30 years down the road you pay the penalty.
Yep.
But it didn't have time to learn that that was going to happen.
Right.
Because it doesn't have any read the literature, it doesn't have any learn from the culture around it.
Right. Yeah, that's potentially a problem. I think this depends on this, where do I put it? This discount parameter gamma, right? If we put this discount parameter so that it does care what happens in 30 years as well, maybe it will actually take time to read literature in order to be sure to optimize the reward also 30 years into the future. But yeah.
That seems like that's what parents are doing.
Right.
I think it was
Yeah.
your teeth you brush
Yep.
to please your parents, not because you're playing so far.
Right. Right. You would have to realize that there is some value into that, but yeah, sure. Yeah. So, what I would like to do now is just have a 3-minute break where you just like discuss with your neighbor if there's anything more unclear, and then I'm going to go on with some other stuff. So just like a 3-minute break.
Because you're